Okay, so part 2, the NRCS unit hydrograph. So there's two kinds, triangular and curvilinear. This is a diagram figure 8.8.1 from your book. You can see the curvilinear hydrograph looks like this and curves around and goes down. The triangular one just starts here, goes up, comes down. So in the last lecture on Intro to Hydrographs, we talked about Snyder's unit hydrograph. We showed that figure from your book that walked through the whole thing. This is very similar, just different equations. How do we take a landscape, a place that we don't have any data for, and create this unit hydrograph for it using the NRCS methods? That's what we're trying to do. So if you want to do the curvilinear method, you can look at table 8.8.1 in your book. In that table, let's see if I can find it here. Table 8.8.1 looks like that. And it's showing you for different portions from the start to the finish what fraction of the total peak is occurring at each of those time intervals so that you can actually draw this curve. But we're not going to focus too much on the curvilinear version. We're just going to focus on the triangular version, because you have to basically develop the triangular one first, and then if you want curvilinear, you can apply these different fractions at these different time periods to it to curve it out. But let's just focus on the triangular for now. So a lot of these are just different equations that apply to different parts of this. So we look at this figure, this time lag T sub L. So this is when the actual storm occurs. It's in this first period. T sub R is essentially the duration of rainfall. The lag is how long is it from the centroid of the rainfall distribution to the peak of the runoff, right? It rains really hard, and then a while later is when we actually see the peak coming down the river, because it takes time for things to all move into the river and run off. So T sub L, how do we calculate that? That's this equation down here. It's L to the 0.8 power. L is the maximum length of flow in the basin. Okay, so whatever my watershed looks like, the maximum length from where the rainfall occurs all the way to where I'm measuring, right? Maximum length that's L. 0.8 power times S, we know S already, the soil storage capacity, plus 1 to the 0.7, divided by 1900 times S percent. This is different than this S. S percent is the average slope of the basin in percentage. So if we have an average of a 3% slope from the top of the watershed to the bottom, 3 is going to go in for that value to the 0.5 power. Okay, so we can plug all that in and get this time lag. Now we have this time of concentration, T sub C. Okay, so T sub C is shown here. It's this time from the end of the rainfall to this inflection point on the curvilinear graph. Now, is it not that important exactly what that is? Just see that this equation is really similar to this one. Just has a different factor right here, 1140 instead of 1900. And that's because they're related, and we'll see that here. So T sub P, the time to peak, this is important when you're trying to draw the triangular unit hydrograph. You need to know how far it is from here to the peak. So that's T sub P. It's equal to T sub R over 2, the duration divided by 2, plus T sub L, right? That's shown right here. We go here, we divide by 2, we go over here, we get to the time of the peak. But part of the NRCS method is that T sub R, the duration, is 0.133 times the time of concentration. So that means the time to peak, if we substitute all that in, is equal to 0.67 times the time of concentration. This distance is 0.67 times the time of concentration. Okay. Now, just as a little aside, the time of concentration is going to be a really important parameter when we talk about the rational method later. It's essentially the same time of concentration we're talking about. Here it's not super important that you know what it means even. It's just a parameter here. But later on it's going to be really important. So you'll hear it again. Okay, so I know now my time to peak, this T sub P, I know how far over the peak is going to occur, but I don't know yet how high it's going to be. Where is this point so I can draw this line from 0 to that point? Well, the peak discharge Q sub P is equal to 484 times A, where A is the area of the watershed in square miles, divided by T sub P, the time to peak. Okay, so that now is going to give me this point, the Q, the peak. And then the last thing I need to know is my time to base, this whole distance from here to here. Once I know how far that is, I get this point and I can draw that straight line. Okay, so time of base is 2.67 times the time to peak for triangular, or 5 times the time to peak for curve. So you can see on this case, our time to peak is 1. So our curve ends here at 5. Here, the triangular, it ends at 2.67. Okay. So in all of these, you might be given, a few parameters that you could use to calculate something like T sub L or T sub C. And then from that, you can derive everything else you need so that you can draw this unit hydrograph. And in the next video, I'll do an example problem to walk us through that.